Okay. Thanks for the introduction and the invitation for me to speak here. Okay. So I will give 3 talks here, and here's the plan for each talk. So I think in the first talk I will explain the statement, and in the second talk and the third talk I will explain the proof. And the second talk will be mostly about categorical trace, and the third talk will be the Clifford algebra stuff, and which has already been mentioned in this talk. Okay. So so first I want to establish the notations. Okay. So throughout the talk, I will use G to denote a split reductive group, and a curve, and both are defined over the finite field. And this G check to be Langlands dual. Okay, so it's a dual group, and it's defined over QL bar, where this L is not equal to P. And here, Q is the power of P. And also the standard notation Bang G over FQ is moduli of G bundles on the curve, moduli of principal G bundles on the curve C, since I will work with Langlands correspondence over the function field, so over the function field, the space of automorphic functions is this space. It's a space of completely supported functions on the FQ points of Bang G. Okay, so it's okay, so it's QL bar valued functions. QL bar valued functions with finite support. So for example, if G is GLN, then this Bang G is just a moduli space of vector bundles of rank n, and its FQ points is can be written as this adelic quotient. G taking adelic point, and the quotient by its the function field value point, and the quotient by this open compact subgroup. So this is really parallel to the adelic quotient over the number field. And in this case, the space of completely supported functions on this stack. Okay, so it will carries an action by the Hecke algebra. So in this case, the Hecke algebra is a completely supported functions on this double quotient S0. Okay, and from the thematic isomorphism, it's a structure with G check, but taking G check a drawing invariant, and I will use HGX to denote this local Hecke algebra. So that's my notation systems. Okay, and so first I still want to start from recalling some basics of the Langlands over function field. Okay, yeah, so the first section, which is Langlands. Langlands over function field. Okay, first I want to recall about this numerical conjecture. I want to call it numerical rectangle. Okay, whatever. Okay, yeah, so the setup is roughly like the following. So suppose you have a G acting on a variety, say for example spherical, and then you can consider this moduli stack. It's called Wang GX. So to formally define it, it's a mapping stack from the curve to X quotient by G, and I think it's already it has already been mentioned in several talks. So it has a map to Wang G, and let me also denote the map from it to the point by P. Yeah. So for example, I think for the purpose of my talk, I only care about this homogeneous case. That is to say, this X is G quotient by H for some reductive subgroup. So in this case, this Wang GX is really just Wang H. Okay, and the map pi is the obvious map from Wang H to Wang G. Yeah, and in this case, I think the relative Langlands correspondence corresponds functional. Oh, there's something unusual. I don't understand. Okay. So in this case, given this, you have a function node defined on the completely supported function on Wang G. You have such a function node, which is defined by sending a function to the value such that you first pull back the function and then push forward along P. Yeah. So strictly speaking, this is yeah. So you have a function you first pull back along pi, and then taking a sum over points on Wang GX FQ. Yeah. So it's really this. Where X takes over all FQ points of Wang GX. Since I have assumed this F to be completely supported, it's always a finite sum here. So I think the story of relative Langlands is roughly saying that, so suppose F is a high eigenfunction. Suppose it's high eigen with eigenvalue, some eigenvalue sigma. It's eigenvalue sigma. Then I should make sense of what do I mean by having eigenvalue sigma. So here, sigma is a G-check local system. Local system on the curve. So in this case, I think the story of pure integral equals L function roughly predicts that so this pure integral should so its value should roughly be something related to L function. where this L is some representation of G check, and this V sigma is okay. So it's the local system on the curve. That is associated to this V and sigma. And I think Yannis has given many examples of this, and yeah, so I won't be very precise about this V here. Yeah, and I also want to remind you that I think this has already been it's already contained in this talk that so in this function field setting, this L function is really something it's not so hard. It's just a characteristic polynomial of the Frobenius. Characteristic polynomial of the Frobenius on the cohomology of this local system. To some corrective power. Yeah, and here I also want to simplify the notation of cohomology of the local system. So here by cohomology I really mean strictly speaking this. Okay, so that's some general stuff, and so for my talk I want to specialize to this so-called Rankin-Selberg case. Yeah, but however, I think the name Rankin-Selberg means a lot. So here I just mean this specific example. Okay, so I take this G to be GLN cross GLN minus 1 and the subgroup to be GLN minus 1. That is diagonally embedded into G. Yeah, and in this case, yeah, so if you want to play with this relative Langlands story, then you need to choose a high eigenfunction f. Since this now G is the product of two groups, so you take okay, so when you use f sigma to denote the function, so you can take it to be a tensor product of two functions, f sigma n and f sigma n minus 1. Okay, so it's a compactly supported function on bound G. FQ. And okay, and so this function has eigenvalue sigma, and where I take sigma to be also a tensor product of two local system, where the sigma n has rank n, and the sigma n minus 1 has rank n minus 1, and both these local systems are irreducible local systems. Irreducible local systems on the curve. But for simplicity, I want to assume they are geometrically irreducible, which means they are still irreducible after base chain 2 to FQ bar. Okay, so this is the setup. Yeah. So in this case, a pure integral should really detect the the convolution L function, which is L as sigma. Okay, so that is to say, now you take this V to be a standard tensor standard, evaluate to the sigma. So it can be written as a Frobenius trace on the exterior, on this exterior power of the comodules of the ecosystem. But if you want to include this variable s, you can make a tip twist here. Okay, so this is the L function. It's just a polynomial in Q to the minus s. Okay, and then this classical theorem of Zagier, Zagier-Piatowski. Zagier-Piatowski, Shapiro, and Shalanka. So in this case, it says that so if you take a pure integral of this f sigma, then you will get this central value of this L function. But of course, this cannot be true because this Hecke eigenfunction can be scaled. So you really need to normalize this function to have Whittaker coefficient 1. That's equivalent to take a product with this Whittaker coefficient here. And I haven't tell you what is the Whittaker coefficient, but it's not so relevant to this talk, so I will ignore it. And okay. Since I'm not telling you the meaning of Whittaker coefficient, I don't need to put any constant here. Okay, so and there's a standard variant of it, which is that you can consider GSGLN cross GLN, and this H diagonally embedded into which is just a GLN, and it's a so-called group case, and you can do a similar story. You take this F sigma to be now you take a Rankin local system, but you take another to be a stew. So so in this case you can still consider this X. But now I think now if you consider the same thing, this will be an infinite sum. But I think it's very simple to fix this problem, which is just to make the period on a single kinetic component. Okay. So this moduli Bang GLN has a decomposition into kinetic components where each component is indexed by the degree of the vector bundle, and now the correct pure integral to consider is that so first restrict it to Bang G0 times Bang G0. Okay, and this integral it's obvious that you can write it as some kind of L2 pairing between F sigma n and F sigma n star, but restricted to this Bang G0. Okay, sigma n star restricted to Bang G0. Okay, so it's just this. Okay, so now it's Yeah, exactly. Now it's a finite sum, and its value will be equal to log q, 1 over log q times the residue. That's equal 1 as adjoint sigma n. And of course times this vertical coefficient stuff. Okay, so okay, and I think, okay, since I'm not telling you the meaning of vertical coefficient, so I need to, so I want to give a precise result. Yeah. So to do that, you can combine these two and get a formula like this. Okay, so now x is still in the Rankin-Selberg setting there. Okay. The following. I think it's a so-called L2 normalization of this formula here. F sigma pair with F sigma dual, and this will be equal to, okay, so let me write down this formula and later you will see a formula for intersection number of some cycles, which looks very similar to this one. Yeah, so we have this residue stuff. That's right, sigma minus. Yes. You mean which one? Yeah, so I think here by x, I really mean that x. Yeah, so maybe let me call this y, okay. Oh yeah, right, exactly. I should write. Yeah, right. It's maybe better to. Yeah. Oh yeah. Okay. Oh, and yeah, and here's still some transcendental factors, not so important. Okay. Oh, and okay, so here by this L tilde, I really mean the normalized L function that makes the functional equation has its simplest form. But since I'm using some not very standard normalization here, maybe let me tell you at least once the meaning of this. It's just because I want to write down precise formulas. Okay, so for this L function, it's a Euro L function times this factor, and for the adjoint L function here, I normalized it in some different way, but it's not something essential. It's just I want to make this this formula compact. Times L function. Here, this chi something is a characteristic. It's all a characteristic of this local system. Okay, so now this is a very precise formula, and okay, so I'm allowed to use this sideboard. So let me use it. Okay, so Yeah, exactly. Okay, so the sigma here really means sigma n tensor sigma n minus. Yeah, exactly. Yeah, and the sigma dual is sigma n dual tensor sigma n minus 1. Yeah. Okay. Yeah, this y disappears because I write this because I write it as this form. Yeah, exactly. Here I mean restricted to the degree 0 component. Yeah. Oh, yeah. Thanks for pointing this out. Yeah. Okay, so now I want to recall you about this first kind of geometrization of it. So this is geometric relative Langlands. I think. Okay, so I think it has also been mentioned in this talk, but yeah. So here I want to formulate it precisely in this setting. Okay, so start from this irreducible local system of rank n. So there's a touched so-called high eigensheaf. It's a sheaf on bound GLN. Okay, it's this high eigensheaf. And so this is introduced. I think it's first defined in GLN case by Wang, and it's proved to exist by Franco Gaskry and Vilonen. Yeah. So and this should be parallel to Hecke eigenfunction. Oh, and so here I'm working with GLN cross GLN minus 1. So I start from this sigma, which is a sigma n tensor sigma n minus 1, and you get Hecke eigensheaf L sigma, which is L sigma n tensor, which is L sigma n minus 1. Yeah. So this is a geometrization of that in the sense of sheaf function correspondence. So this has a natural wave sheaf structure, and you can take the trace of Frobenius on it, and to get back to this Hecke eigenfunction as sigma. Okay, and so in this case, this pure integral has obvious geometrization given by so I still have a map pi there. Okay, so it's given by first pull back this local system. First pull back this Hecke eigensheaf and then take compact polar cohomology. Yeah, so and I want to call it and I want to denote it in a way that is parallel to the notation here. Yeah, and so the previous formula is relating this with this, and this also has obvious geometrization, which is this exterior power of the first cohomology of the local system. But take a twist with 1 over 2. And, okay. So yeah, this is a geometrization of that in the sense of taking trace of Frobenius of this get this. Okay, and now it's okay. So in this geometric setting, it's a theorem of Lysenko. Theorem of Lysenko says that says that this will be isomorphic to this. Isomorphic to this. In what sense they are isomorphic? So both are vector spaces and carries a Frobenius endomorphism. So this isomorphism really means that these two structures are isomorphic. Okay. Oh, and of course, so as in the classical setting, you have the issue of you have this issue of vertical normalization here. So this can't be literally true. So yeah. So I think yeah. So you really need to put a condition here, which is that the vertical coefficient of L sigma is kind of isomorphic to this QL bar. Okay, so that's some vertical normalization issue. Yeah, and okay, so this really geometrizes this formula, and I think it's also a theorem of Lysenko, which which geometrizes this formula. Okay, so yeah, okay, so the correct, okay, so I think you can guess this form. Yeah, yes, so you start from this Hecke eigensheet and tensor product with this dual, and take compactly supported cohomology on the this kinetic component, and this should geometrize this. Here the theorem says that okay, and then you need to find something geometrizes that residue. So the correct thing to put this here. Okay, it's the cohomology of this this adjoint local system, and take twist by one and take symmetric power. Oh, and here of course, so for even degree cohomology, the symmetric power means symmetric power, and for H1 it means exterior power. Yeah, but to see that residue, so you need to invert some element here. Say this Xi, so this Xi lies in H2 of adjoint. H2 of adjoint sigma n, which is isomorphic to QL bar. I'm probably ignoring some take twist. Okay. Oh, okay. So these are the these are the geometrization, this kind of results that I want to mention, and I think what Yannis have been talking about is really a family version of this. Yeah. So here I'm fixing some L parameter and study this pure integral, and I think the conjecture of beta SV is really a family version of this, but here I want to state this result explicitly. Okay, so yeah, right. I think if you take traceable frobenius of this, you get this.
Yes, how do you see this Q?
Of this Q, log Q. I think. So I think in this formula you don't have log Q, right? And the log Q only appears here, and that's because this residue operation is yeah, I think this residue operation is transcendental, and that and that cancels with this log Q. Yeah. I think it's just because I want to. It's just because I want to write this formula. using this residue. I mean, no, not something essential. Yeah. Okay, so yeah, so now I want to come to the main thing, which is I don't know how to call it. Maybe let me call it arithmetic relative Langlands. Here, arithmetic is. Okay. So I think so I think the classical Langlands correspondence studied this double quotient space, this adelic quotient, and so there's one way to geometrize this over a function field. That is to take this moduli stack Wang G. But there's another way to geometrize this, which is this Schmor variety of G. So here, by Schmor variety, it really means it's integral model. So very informally speaking, let me regard it as something defined over Z. Yeah, and so there's some analog of it over a function field, which is called the moduli space of Shtukas, moduli space of GShtukas. Yeah, but to define them, you need some extra tries, and it will be a moduli space defined over a power of the curve C. Here, this new underline is a sequence of co-weights from mu1 to mu_r, which is a sequence of co-weights. Okay, so I will recall some basic basic things about moduli stack of Shtukas later. Okay, and in the classical settings, you consider functions on this Wang G of Q, and they will be replaced by cycles on this moduli space of Shtukas. And so previously, you have something relates the value of L-function, and I think it's a very important observation starting from Galois and Zagier. Here, you really should see some derivatives of L-functions. Some derivatives of L-function. Okay, so I think, this is what I mean by okay, yeah. So now I want to spend some time talking about this moduli space of Shtukas. Okay. So section 2.1 is about Shtukas. Okay, so the Shtukas are defined in the following way. So there's so you have this Hecke stack between Wang G and Wang G. Oh, so here let me first put 1 mu here, where here you have 1 mu, which is a dominant co-weight. So this Hecke stack is a moduli space of 2 G bundles, so E0 and E1, but you fix some an isomorphism between them on C, but with 1 point removed. Okay, so this is the moduli. This is a Hecke stack, and here you will have a pole on the point C, and you can bound the pole by this multiplication type mu. Okay, So you have this Hecke stack, and you can consider this iterative Hecke stack as so less or equal to mu underline. So here mu underline is the sequence of mu, and so it's just defined to be a fiber product. Hecke G less or equal to mu1, and fiber product over Wang G is less or equal to mu2, and so on. And I want to name these two maps by Hecke left and Hecke right. And Hecke left just send it to E0, Hecke right send it to E1. And this Hecke stack, it also has a map to the curve, which I want to know this map by L, which means lag. Okay, so you have this iterative Hecke stack here. It also has two maps to Wang G. And it has a map to R points on the curve. Okay, so the moduli space of Shtukas is really a fixed point locus of this Hecke correspondence, but you twist it by a Frobenius. Okay, so you have this Hecke stack, and it has two maps to Wang G. One is Hecke left, and another is Hecke right, but you compose with Frobenius. So the moduli space of Shtukas is the fixed point of this correspondence. So if you haven't seen this before, so I think one important example to keep in mind is that, so suppose this R is 0, that means you don't allow, is that you don't put any mu there, then what this diagram, so this Hecke stack is really just Wang G itself, and it has two maps to Wang G. These two maps are just identity and Frobenius, and if you take his fixed point, it's then you just get back to FQ points of Wang G. Okay. So in this sense, you see that this moduli space of Shtukas are really some kind of generalizations of FQ points of Wang G. So I think the most important thing about this moduli space of Shtukas is that so if you consider it as compactly supported cohomology, but you need to consider some kind of intersection cohomology. That's the most canonical thing to do. It also carries an action by the Hecke algebra. Okay, so this also realizes the Langlands correspondence. So suppose GSGLN here, then this moduli space of Shtukas is non-empty. It's non-empty if and only if the sum of all mu i's lies in the maximal torus of ICLN. Okay, so here I just want to state some very basic properties of this moduli space of Shtukas, and this moduli space of Shtukas has a kinetic component decomposition, which is still in terms of degree of one of its vector bundles. Okay, so that's some basic properties. This moduli space of Shtukas, so I have just said it realizes the Langlands correspondence in the following sense. So you consider it's compactly supported cohomology, right? since it carries the action of the Hecke algebra, you can make sense of its sigma n isotopy part. Here's one thing you need to pay attention to, which is that, okay, so this compactly supported cohomology is a direct sum rather than a direct product. And here, if you take some isotopy part, then the isotopy part must spread to all kinetic components. So you really need to put a direct product here. Okay, so here by isotopy part, I really mean the isotopy part in this direct product. And so the most important thing is that this will be isomorphic to something very concrete associated to the local system, which is, okay, so you have a mu underlying, so you need to see some mu here. Okay, so for mu, you have this highest way representation v mu I, and you can evaluate on the G-check local system to get a local system on the curve. And you take its cohomology and take tensor product over all I. Well, yeah, so this is a description for its sigma isotopy part. So of course, I'm still assuming this sigma to be some very good parameter. And in particular, you see that this is finite dimensional. In this sense, the cohomology of Shtukas realizes the Langlands correspondence. Okay, so I think so far it's all this basic stuff. And okay, so now I can start to talk about the special cycles. Any questions so far? Oh yeah, right. I think yeah. Okay, so now let me turn to cycles on Shtukas and to talk about the special cycles. So I think previously, so you care about this. Okay, so I think I've already explained that the compactly supported function on Wang GFQ will be replaced by the compactly supported cohomology of Shtukas. Okay, and so before you consider some high eigenfunction, but you know that function is only well-defined up to scalar. So what you really care about is a one-dimensional vector space that is generated by this function. That is to say, you're considering the sigma isotopy part. So here for Shtukas, you also have this sigma isotopy part. And so before you're considering a pair which comes from a map from Wang H to Wang G. So for Shtukas, so the analog is a map from Shtuka H to Shtuka G. So you need to fix a sequence of co-weights for H, mapping to a sequence of co-weights to G. So here, mu underlying H is, as I said, is a sequence of co-weights of H, and this has a map to co-weights of G, and you require that this mu underlying H will be mapped to mu. And assuming this condition, you will have such a map. And here, this map is denoted by pi. Here, let me call it pi Shtuka. Okay. Yeah. So before you are caring about somehow in some sense, the push forward of the characteristic function on Wang HFQ. Right? So for Shtuka, the correct analog of this is to take the push forward of the fundamental class of this strip H. Okay, but it's lying in which space? So I should say that it lies in the Borel-Moore homology of the moduli space of Shtukas. Yeah, so what do I mean by Borel-Moore homology? So it's really, so I think you can take this definition as the dual of the compactly supported homology of Shtukas. Yeah, so I think, yeah, exactly. So I think as before, so this defines a functional on the compactly supported function on Bang G, and here it's the same, it defines a functional on the compactly supported homology of Shit G. So these are parallel to each other. And before you, right, yeah, so before the formula that I wrote here can be, can roughly be stated as, okay, so you have this push forward of characteristic function, and then you can restrict to the sigma isotable part. And on this sigma isotable part, there's also, you can also restrict the L2 pairing to this isotable part. And what you do is, it's really you are comparing these two elements with the L2 pairing. So you're really considering this stuff, and so in precise. Okay, so it's precise since it's understood in terms of that formula there. Okay, so for general mu, you should put some IC here and here, but in the case that I will talk about, I will always fix this mu to be minuscule, and it will be the constant sheet. Yeah. Okay, so the formula above just says that, okay, so this is related to some L function, something related to L function, and okay, so the parallel statement for Shtukas of this should be like the following, right? Okay, so this pi should lower Schritt of the fundamental class and pairing, and suppose you can restrict it to the sigma isotype part and take some kind of intersection pairing with itself and restrict it to the zero kinetic component. Okay, then I think, so the formula I will be talking about is that it's something related to the R's derivative of the L function valued as the center. Yeah. Yes. Yes. Thank you. And I think this kind of phenomenon should first of course motivated by the Zagier formula over the number field and over function field. So first formula proved. First formula of this kind that get proved is in the work of Zhang. Their work is in the setting that G is PGL2. So this H is a non-split torus. Okay. So I think yeah, right. So, and I think note that so for this story to make sense, you want to take the intersection number of this cycle with itself. That requires the cycle has half dimension of the total space. So you need this condition that the dimension of Shtukas H and U underline H is half of the dimension of Shtukas G in mu on the line. So you may think that, okay, so here you have a lot of freedom to choose this mu, but however, this condition is very strong. Yeah, say for example, if you are in the Rankin-Selberg case, so this already forces it already forces twice of that mu on the line, and that's what I'm that's now what I'm going to talk about. So, okay. Yeah, I said that. So if you want to intersect the special cycle with itself, yeah, to get the number, you need this condition, but this condition turns out to be very strong, especially in a strongly tempered cases. So, okay, so.
Why do you see the value of 1/2 instead of the rest of 1?
What do you mean here? You mean why I see the central L value? Or
yes, it's one of the correct things to see that you can't instead of Shtukas, right?
Yeah.
And that instead of this other value was at 1 instead of this.
Yes, in this. Okay. Okay, thanks. Okay, so now finally I'm ready to state the main result. So I want to formulate it in a precise form. Okay. Yeah, so now the main result. Okay. So as before, I fixed the specific twice of G and H, which is GL minus 1 as before, and the sigma as before. And still, I assume that both local systems are geometrically reducible on the curve. And so it turns out that this condition, this dimension condition, well, forces your twice of mu. So so basically, you only have the two choices. The first mu plus is this standard one, and mu minus is a dual standard one. Okay, so you have these two co-weights of H, but I want to abuse notation and also regard them as co-weights of G. Okay, so use this co-weights. Right, but you need a sequence of co-weights. That means you can, here I mean, okay, so for each sequence of signs, you will get a sequence of co-weights in terms of this and this. Okay, you'll get a mu epsilon underline, which consists of mu1 to mu epsilon 1 to mu epsilon r. Okay, it's a sequence of co-weights of H. Okay, so that's our choice of co-weights. So given this, you have this map between the moduli space for Shtukas. So it's pi Shtukas from Shtukas H to Shtukas G. Okay, and now if you compute the dimension, you will see that this moduli space has dimension 2nr. and this has dimension nr. So it's really in this middle dimensional setting, and I think if you do some simple computation, you will realize that so for that condition to satisfy, this is the only possibility. Okay. Okay. So here I think I've already introduced the notion D, that is degree of vector bounding. Okay. So right. Then the cycle class I considered is this cycles. VD is defined to be the push forward of the fundamental class of Shtukas H. Okay. Yeah. So now it's some middle dimensional Borel-Moore homology class. Okay, so these are what I mean by special cycles. So you also have this intersection pairing, which is a bilinear form on the middle dimensional cohomology of Shtukas. But I think as before, you restrict it, you only consider it on a single kinetic component, which is this degree 0 component. Okay, so it's this tensor square to Q bar. Okay, so this is the intersection pair. Okay. Yeah. So now you see that okay. So as I said, the condition is strong. You only have these choices of mu, but you still have lots of choices here. So it turns out that the correct thing to do is to put all these choices together. So I define this mr mu, this mr sigma to be the direct sum of all isotypic parts. Okay, so all isotypic part, but with different choices of this mu. Well, middle dimension cohomology, Shtukas, mu epsilon underline, and the degree D. So recall that to make sense of this isotypic part, you need to take product over all degrees and take isotypic part and take direct sum with respect to all choices of signs. So this is the sigma isotypic part. And as I have already mentioned here, so this thing is actually very explicit. So this space is this thing here is isomorphic to. So suppose the sum of all the signs is 0. So suppose the sum of all the signs is not 0. Then in this case it's 0 because the Shtukas is empty. So if the sum is non-zero, suppose the sum is 0, then what you get is really the cohomology of the local system and that tensor to some power. Okay, so this is just this. Okay, so that's the isotypic part. Okay. Yeah, okay, so now I'm ready to state the main theorem. What the power means, okay. Yeah, so suppose the epsilon is 1 and minus 1, I really mean that vector space tensor with is due. I think that explains the meaning of that notation, yeah. Yeah, so suppose in general you have a sequence of signs when you have 1, you tensor, minus 1 tensor with is due. Okay, so now finally the main theorem. So I will assume that P is greater than N. So first, so I want to study this special cycle. That cycle V here restricted to the sigma isotopic part. So, right. So you have this cycle. And restricted to the isotopic part. But you take the sum of all the cycles. Sum is taken over all these choices of multiplication types and all degrees. Now you see that this involves an infinite sum. Yeah, so the first statement is to say that this is a finite sum. This is a finite sum. Okay, so this procedure is really well defined. And the second thing is that, okay, so recall that you also want to restrict your intersection pairing to the sigma isotopic part, and you want to pair this element with respect to that pairing, right? But you see, these elements are some elements inside the dual space of this MR sigma. So there are some element in this MR sigma dual. But this intersection pairing, so if you can of course restrict it to you can of course restrict this intersection pairing to MR sigma and tensor with MR sigma dual. So why I do this restriction? Because you know the intersection pairing is supposed to pair between sigma isotopic part and sigma star isotopic part. So do this restriction. But this is a bilinear form on. It's a bilinear form between MR sigma and MR sigma dual. So, okay, yeah, so here the problem is that this form is defined on this vector space, but the elements you want to pair, they are really dual vectors here. So to make sense of pairing of dual vectors, so you need this pairing to be non-degenerate. Okay, so the second statement, this is non-degenerate. Okay. So once you have a non-degenerate pairing, you can pass it to the dual space. So you get a pairing between MR sigma dual and MR sigma dual. It's dual non-degenerate. Okay, yeah. So now it makes sense to talk about this intersection pair. So you have this VR sigma, so you can pair it with this VR sigma dual. The pair is understood. It's understood in terms of this bilinear form. Yeah, so now this is a well-defined number given 1 and 2. So the statement says that, okay, so this is this is really higher derivative of L function. So what you see is the R's derivative, the central value of this Rankin-Selberg L function of sigma and sigma due. But okay, since this is some kind of L2 normalized conjecture, it's an L2 normalized formula, so you still see this adjoint L values here. Okay, and for these values, you don't see derivatives or something. But okay, there's still some factor of Q, the dimension of bound H. And there will also be some transcendental factors which are not interesting, and they are just because I want to write things in terms of derivative and residue. Just nothing very essential. Okay, so this is the statement of the main result that I want to present. The proof in the last two talks. Okay, so far is there any question about the statement? Okay. So suppose there's no question. Let me yeah. Yeah, exactly. This doesn't. Yeah, exactly. Because GLN doesn't have small variety, but I think you can replace. GLN by unitary group. I think there's analog of this. I think I'm not very familiar with that story. I think there's conjectures in that way. I don't know if it's true or not. Yeah. Yeah, exactly. Okay. Okay, so now let me make some remark about this theorem. Oh, yeah. Yeah, exactly. Oh, yeah, I see. So you want to write down a formula without doing the sum, right? Yeah. So I think I can still write down a formula for them, but it will not be related to the kind of L function that I can recognize. Yeah. Yeah. I think later in the proof, I think later you can see through the proof that what those numbers are. Yeah. Okay. So yeah, now let me make some remarks about the theorem, and then I will end my talk. So okay, so first let me compare it with the previous result of Yu and Zhang. Okay, so of course, previous result is G is PGL2. And H inside it is a non-speed torus. So in particular, it's a restriction of scalar from a two-folded cover C tilde to C of Gn, and quotient out by Gn. Okay, so this case it's proved by Zhang. But their method is somehow completely different from the method using here. So their method is using relative trace formula. But okay, okay. So now maybe let me make a few remarks why this relative trace formula is a little bit difficult to be applied here. So the problem is the following. So what's the meaning of using RTF? So it means okay. So here you want to detect the intersection number between this isotypic part of special cycles. Then using RTF really means that you want to so instead of passing to isotypic part, so you want to study the intersection number of the entire cycle with Hecke translate of itself. So you apply a Hecke operator to this cycle, and then take intersection pair. Yeah, so using RTF really means that you want to understand these numbers and compare it with another setting and to understand these numbers. But however, the problem is that this cycle VR. Okay, so this intersection number makes sense. Makes sense only if the Shtukas of H is proper. Okay. Yeah, because if this is not proper, it doesn't make sense to talk about its intersection number with itself. I mean, it's too non-proper thing. You have very serious convergence issue. So in this case, this Shtukas H is really proper. So yeah, so you can use this RTF. Use this thing to do, but for this higher dimensional case, it's a bit hard to apply this method. Yeah. So, right. So the actual proof I'm going to give is so the proof idea is this. So there I have stated this kind of geometric relative Langlands result, geometric. And you want to deduce this kind of arithmetic relative Langlands. Okay, so the idea is to deduce this arithmetic version from this geometric version through the tool of categorical trace. Okay, so yeah, I think in the next talk I'm going to focus on this categorical trace stuff and see how you can reduce this this formula. Okay, so strictly speaking, how you can reduce the study of this special this isotypic part of special cycles to some question that is related to the to the geometric version there, and then in the last talk, so I guess I'm going to explain how this higher derivatives actually show up via the Clifford algebra action. Yeah, I think that's how I want to talk about.